for photovoltaic applications in the research of fundamental properties of quantum effects in both semiconductors and low-dimension structures. So, Professor Leitão has participated in several projects. Project 13 has been checked before, and he has 2 ongoing projects right now in the field of this area that he's going to talk to us about. So,
the title of the talk of Professor Leitão will be Optical Characterization of Nanostructures in Thin Fields for Solar Cells Application.
Thank you very much. First of all, thank you very much for the invitation and for giving me this opportunity to present recent work that is belonging in the Physics Department I3N. I will talk mainly about optical characterization of nanostructures and thin films for solar cells applications. I will also briefly address structural properties for both cases. The outline of my talk is here. I will start by magnesium carbon nanowires. I will describe briefly the growth of nanowires and the morphological and structural characterization. And after that, I will concentrate on discussion of relative and non-relative positions. After that, I will discuss from literature influence of doping and compensation levels on optical properties of coperites and casterites. This is some kind of introduction for the other topic that I will present some results, CZTS based on solar cells. Here I will start by the growth of the thin films and the solar cell structure. I will address also the structural characterization, and I will finish with the PL characterization. Concerning the application of nanowires in solar cells, in literature there are different approaches. Here I present 3 different approaches. Here we have a radial PN junction. We can have a PN junction along the axis of the nanowire, or a PN junction between the nanowire and the substrate. In our case, we are studying nanowires copied with magnesium, because in this case the nanowires are of P-type doping, and we will cover the nanowires with another material, normally cadmium sulfide, and in this case we are creating perpendicular to the axis of the nanowire PN junction. This PN junction obviously is a fundamental part of the solar cell. It's what allows us to separate the charge carriers in the solar cell. The carbon nanowires were grown by molecular being epitaxy. We considered 2 different substrates, galvanum cyanide 11B. Here the combination corresponds to arsenic atoms, and silicon 111. The growth of nanowires was performed using gold colloidal nanoparticles. Some of the regions of the samples were covered with these gold nanoparticles. Around these regions, so here, we have the growth of an epitaxial layer with a few hundreds of nanometers of thickness. I must mention that underneath the nanowires we still have a thin epitaxial layer with a few tens of nanometers. And I will address also this problem in the XRD measurements. Here we have same image in which you can see that we have a mesh obtained with non-vertical nanowires. The dimensions are very large. We can have lengths that extend to a few tens of micrometers, and the diameters can vary from several hundreds of nanometers at the base of the nanowires, as you can see here, for example, up to a few tens of nanometers at the end of the nanowire. We can see that for the growth on galvanum spots, but the density is clearly lower. Here I show 10 images in which we can see that the dominant crystalline structure of nanoiris is mosaic. We can see here corresponds to these regions of the nanowire. And we observe the occurrence of the setting effects that corresponds to the presence of zinc-vein gallium cycle. In this high resolution image, we can see that in the region of the defect here, we have the stacking alignment typical of the zinc-vein, and in the large segments, we have the stacking alignment corresponding to the website. These results were confirmed by grazing incidence measurements performed with XRD. We concentrated mainly on this range of angles here, in which you can see the three different reflection peaks. These peaks here, the one on the left and the one on the right, have origin just in the reflections from the Burzite crystalline phase, and the peak here in the middle has two contributions, one from Burzite and another one from zinc-vein. So, due to the fact that we have underneath the nanowires the presence of an epitaxial layer, when we are trying to study, to investigate the nanowires by X-ray diffraction, we have always the influence of that epilayer. So we try to reduce the incidence angle here, as shown here, in order to try to avoid precisely the influence of that epitaxial layer. We observe that as we reduce the incidence angle, we see that relative intensity at this peak diminishes clearly, and relative intensity is more or less close to the relative intensity of the other two peaks. The contribution from the Burzite must come just from the gallium arsenide nanowires. Okay? Why? Because in the epitaxial layer, as far as we know, until now, no one was able to grow Burzite gallium arsenide. So these results confirm these results from there. From this structural characterization, we predict a band bending at the hetero interface, in which we should have quantum wells for electrons, as shown here. If the thickness of these quantum wells change, obviously the fundamental level for the electrons should also change, and that will have an influence in the energy and relative position that we will observe, for example, in photoluminescence measurements. We perform cataloguminescence measurements on this on the field of these nanowires, and we see that as we put the detector of the equipment at a particular energy value, we observe a stripped emission along the axis of the nanowire. We see that for each particular energy, we have the emission from different regions of the nanowire. So this is compatible with this picture that we have here. Concerning the PL, we know that this is a very useful technique for the characterization of the electronic level structure in a superconductor. Here we have the two PL spectra for the two different samples. Sample A for the growth of the nanowires of gallium arsenide, and sample B for the growth of silicon. We observed mainly positions between 1.4 and 1.52 electron volts, and we performed the fit with Gaussian components in order to try to describe the position of each transition and the relative intensity for each component. The investigation of the excitation power and temperature dependencies allow us to study the nature of the relative positions and obviously the non-relative know that when we have values of n lower than 1, we have combination mechanisms involving charge carriers with some degree of localization. For example, if we have charge carriers localizing on defects, as we can study, for example, in bulk materials. And when we have the n values clearly higher than the value of 1, we have transitions involving accidents. In our case, we obtain these values, and we see that these estimated values of them are compatible with type 2 transitions. I didn't mention previously, but maybe it's better to return here briefly. These type 2 transitions correspond to transitions in which we have charge carriers in different special positions of the semiconductor. Okay, so they are indirect in the real space, as you can see here. So this axis here corresponds to the position element of the material. Another need comes from another need for this type of transitions comes from the dependence on the excitation power of the peak energy of the transitions. The experimental points are shown here, and it can be shown that for type 2 transitions we have a proportionality between the ground state energy of the electrons and the values of the excitation power. And the relation is the one shown here. The observed linear behavior shows that the observed transitions can actually be of type 2. This is more easily seen for the sample A, and for sample B we have some spreading of the experimental points, in particular for this particular value of excitation power, and we see that we have some deviation of a particular point, but in any case I think we can take this conclusion from two samples. Concerning the dependence of the PL intensity on the temperature, we have here the experimental points for both samples. We perform it fit with the common theoretical equation that is shown here. This term here corresponds or describes the involvement of discrete energy levels. So this equation describes the activation of non-radiative de-excitation channels. Okay, as we increase the temperature, the intensity is decreasing, as you can see. Okay, and this term here, the third term, corresponds to the involvement of that. The best model gave these activation energies that are shown here, and we see that the values, or we ascribe the values of the activation energy involving the band to the release of the electrons from the zinc band segments. It corresponds more or less to these values. At least this is our interpretation. The higher values of EV, these values here, estimated or obtained for the growth on silicon, suggest that zinc band segments, in that case, for the growth on silicon, are higher than the segments obtained for the growth on gallium side. So it corresponds basically to the difference between these two segments shown here. Finally, we investigated the dependence of the peak energy on the temperature. We observed that, with exception of this component for higher energies here for sample B, all the other components follow roughly the reported data for the dependence of the zinc blend phase of arsenide with temperature. This dependence is shown here. It corresponds to the Hassler equation. This behavior is compatible with type 2 transitions, and the difficulty for So, moving now to the influence of doping and compensation levels, I will present some results from the literature that I think will help the interpretation of our data. We know that the electronic level structure of the semiconductor depends critically on the doping and compensation levels in the material. I will start discussing precisely using a gallium arsenide layers. This work is from 1977, and I think it's very good work. You consider different samples in which we can see that the carrier concentration is increasing as we decrease the element table. After that, he studied the dependence on the excitation power, the peak position of the different bands observed by him, and we can see that here, if we consider these samples with a low carrier concentration, we have a very small shift to higher energies. Okay? However, when we increase the doping, we see that the shift is clearly higher. Okay? You call it these bands moving bands. Okay? It's interesting. In my opinion, it's interesting the name he gave to this. This behavior was related with irregular fluctuations of electrostatic potential with position, due precisely to the presence of charged impurity atoms and fluctuations in the concentration of these impurity atoms. And one of the important points is that the impurity atoms, in the case of gallium arsenide or in the case of CCP, as I will discuss next, the defects must be and should be discharged. Okay? He discussed this behavior considering this figure here, and for small values of the shift, the parameter beta that I mentioned previously here, I think I forget, the shifts are shown here, corresponds to this parameter beta there. So we see that as we increase the doping level, the values of beta are also increasing. So for small values of the shift, radiative transitions involve discrete energy levels, and for higher values of beta, the fluctuating potentials clearly influence the radiative transitions. This is the pictures that we proposed at that time. The deviations from stoichiometry in chalcopyrites and castrites results in a clear change of the shape and the full width at alpha maximum of the observing bands. We have here an example for copper indium gallium selenium 2, CIGS. We see that for the copper-rich fields we observe more or less thin bands, and several of them are observed. As we change from copper-rich to copper-poor fields, we observe just an asymmetric band and relative band. The changes in the TL are related to the deep modifications in intrinsic effects, densities, density of the effects are created obviously for each composition, and we have that influence on the TL. The structural modification in the films is reflected in the behavior of the TL precisely under the change of the excitation power as we discussed it, for example, for the case of gallium arsenide. Also, in this case, for CIGS, we see that if we have copper-rich fields, as shown here, for example, we see that the value of beta is very low, but when we start seeing copper-poor fields, we start observing that these values of beta clearly increase. So when we change the excitation power, we observe in our PL spectrum a shift at the radiative transitions. In copper-rich fields, radiative transitions are ascribed to a combination of excitants or bond acceptor pairs. And in the case of copper-poor fields, we are assuming the presence of fluctuating conditions. So, deposition by helium RF magnetron scattering evaporation of precursor layers on any automotive soda-like glass. The precursors were sulfurized at a high temperature, 1 minute for sample A and 2 minutes for sample B. The structure of the solar cell is shown here. We see the molybdenum, CCTS, CDS, and the layers of the TCO that finish the cell. The structure characterization of the samples shows that we have mainly the CCTS phase and we have a copper poor thin fields. Concerning the PL, we observed a broad band and a symmetric band. For the dependence on the excitation power, we observed precisely very large sheets, in this case blue sheets, and for the dependence of the PL intensity on the excitation power, we obtained these values that are shown here. How many minutes? Okay, so I will finish quickly. Here we have the dependence on the temperature, PL peak energy, and the PL intensity here. And we also tried to investigate if we have the possibility to have donor receptor pairs in these samples. We tried to fit this equation, and we observed that it's not possible to use this model to describe our results. And finally, the model that we proposed to describe the broadband that we observed is this one. This is quite different from what we observe in lightly copied semiconductors. So we have heavily copied and compensated semiconductors, and the relative transitions that we are observing involves the binding of an electron in agglomerates of donors with pools connected to receptor levels that follow basically the fluctuations in the bands. The presence of fluctuation potentials is one of the limiting factors for the solar cell efficiency. And to finalize, I would like to acknowledge several colleagues that collaborated in this work, many of them from the University of Aveiro, but also University of Cádiz, where the measurements were performed, Lund University with the cathode emissions measurements, and Universidade Federal de Minas Gerais, where the gallium arsenide nanomaterials were from. Thank you very much for your attention.
Okay, thank you very much for your contribution. We have time for a very short question so that we respect the timetable.
In the first part of the talk, I thought that the idea was to have aligned forest or aligned rocks. But in fact, most of the rocks were not aligned.
Yes, it's not. It's not easy to control the alignment of the gallium arsenide nanowires. I think I'm trying to show this same image. We think that you can see in both images that the epilayer underneath the nanowires is not a flat epilayer. So we have two problems. We have not a flat epilayer in one side, and in the other side we have the lattice mismatch. In this case, for example, that is in terms of the technology is the most important case because it's the growth on silicon. We have the lattice mismatch between gallium arsenide and silicon. So probably we have polycrystalline epilayers, which is a problem to the vertical alignment. Okay, but in any case, for the application application solar cells, maybe this is not a problem, because we will have different orientations of the nanowires. So when we consider the incidence of solar cell, solar light, we have different configurations for the different nanowires. So maybe one is not able to absorb that light, but another one in the bar would probably help do it.
Okay, I'm sure during the coffee break, please stay. We can have more time for further discussions. So we would move on with another guest speaker, now from CESAM. CESAM is the Center for Environmental and Marine Studies. Dr. Susana Loureiro. Please, Susana.
Dr. Loureiro obtained a degree in biology and a master in ecology at the University of Coimbra and a PhD in biology at the University of Aveiro. She is currently an assistant researcher at the Department of Biology CESAM, and she has been the recipient of several awards, and I would like to highlight the 2007 CETAC Special Award for the Outstanding Contribution for the Environmental Society. This prize was awarded by the Society of Environmental Toxicology and Chemistry. Her main interests are the application of methodologies to legislation like REACH, the Water Framework Directive, and also to contaminated soils and waters, environmental risk assessment, stressors, effects on biodiversity, and evaluation of water and soils contaminated with chemical mixtures in water and soil. She had active participation in 16 projects, and she is now participating in 3 projects.
So today, Susana is going to tell us about the nanoparticles and the environment, behavior, ecotoxicity, and fate. Yes.
Thank you very much. First, I would like to acknowledge and thank you for the invitation for being here today. So I will mainly give you our approach, or the way that we approach nanoparticles and the way that we improved our approaches, considering that some years ago people working in the environment or that have some concerns regarding the environment, usually we dealt with metals or pesticides, organic compounds, and then after we had the opportunity to know nanoparticles and their specificities, we had to go for further approaches, change our ways of evaluating toxicity. So mainly I will try to explain how we deal with all these changes. So first we knew that since the beginning all the organisms have been already exposed to several nanoparticulate matters. So there are several records for nanoparticles, natural nanoparticles present in the environment. Organisms, aquatic or terrestrial organisms, have already to deal with them. Even us, humans, we have to deal with them, the natural ones. But the main problems were regarding the manufactured ones. So, although a lot of people don't know that they are all around in the majority of the materials that we use daily, we can find them in several products. So here we see daily creams that we use at home that contain nanoparticles, tissues for sporting clothes especially that have nanoparticles, but then we have nanopesticides, we also have nanofertilizers that can be in contact with organisms that usually are not aware of this kind of particles. So within these, the Horizon 2020 also sent out some calls, mainly on the characterization of nanomaterials and nanoparticles, and in order to change them in a safety way, so we could have a sustainable and safe production and use of nanoparticles. So this, as you know, is a great effort between the academia, industry, and stakeholders. This is somehow easy if you think about mainly these audience here that are used to this kind of particles, the way they behave. But for us that work in the environment and that are not used to this kind of particles, sometimes it's difficult to explain toxicity. Another issue that we care about is where these nanoparticles fall into in terms of legislation. So we have the REACH legislation. There is a general one where we know that nanoparticles can be included as another chemical. Within the REACH, we have some constraints where production tonnage is included as one of the factors. So if an industry produces less than 1 ton, there is no risk assessment needed to be done. On the other hand, the same nanoparticle can be used for several purposes. So here we have, for instance, the food additive legislation, we have the cosmetic legislation, we have the biocide legislation, and the REACH. So regarding these, for each use, you have to apply a specific legislation. So this also is a little bit tricky when we try to approach and to evaluate the potential risks to the environment, to choose which legislation to use. But within this also the OECD has devoted some effort on adapting already existing regulatory frameworks in order to adapt them for the new specificities and the new properties of nanomaterials regarding mainly testing, exposure assessment, and risk assessment. So there are already being made some efforts to adapt the already existing methodologies. So the first thing that we usually think about is the emission scenarios, and within these the exposure scenarios. So this was the framework of the FP7 NanoFab project, where we start studying the toxicity and fate of nanoparticles to the environment. And here is an example of a cosmetic product that can be used, and after showering it will go down drained and suffer treatment in wastewater treatment plants. Depending on the country, there will be different ways of treating this kind of waste, and then they will come out of the treatment into different matrices, the effluent and the sludge or the biosolids, and then the effluents can be discharged to the aquatic systems, and the biosolids are often used as fertilizers in agriculture, or can be disposed in the soil or on the topsoil. So another approach is now thinking about pesticides. Nanopesticides react completely different, like the ones that we knew, the previous ones, the regular pesticides, and also nanofertilizers. So they have new components, new behaviors, and we know, of course, they will end up in the soil. But regarding emission scenarios, we cannot disregard another possibility that are the runoffs. So when it rains a lot, you'll get some water logging, and then this water can go for the aquatic systems, so it will be another source for pesticides, nanopesticides, nanofertilizers into the aquatic systems. So this is what we think about when we are trying to decide which one will be the better approach to use. So the characteristics that make these nanoparticles special are those also that can make them potentially hazard to environmental species. So, as I told you before, first we only thought about concentration. We were based on Paracelsus, that the concentration and the dose will make the poisoning, but now we have to deal with other components like shape, size distribution, the surface charge, if they are functionalized or not. And you have to believe me that for us, for instance for me, a biologist, this is very complicated. In the beginning, it's hard to get into this, it's hard to get into this all type of specificities to understand how these characteristics will influence the toxicity, because they will influence their behavior within the environmental metrics they are included in. So one of the main issues in terms of deciding if a nanoparticle is toxic or not, and here again we are dealing with another issue, that is dissolution. So first we thought we were just dealing with a new material, so a nanoparticle, but then we just got the dissolution phase. So now we need to decide if the toxicity is more related to what is dissolved from the nanoparticle, or if it's mainly part of the nanoparticulated form. Sometimes, or the majority of times, it's a combination of both, but it's difficult to approach this kind of issues. And we also know that this dissolution is also related to all those properties from the nanoparticle. So if you want to design a nanoparticle to be safe and sustainable, you have to get all these characteristics into a play, and then if you change one, of course you will change all the other ones and we have to restart again. So for us to think about all these is tricky and it's difficult for the approach needed to be followed. Another issue, as you all know, is aggregation and agglomeration. And for us it's very difficult to characterize our exposure, because usually we need to understand the exposure to understand the effects. And if in time, 1 hour of exposure, we have these, after 4 hours we will get something like this. And then after 24 hours we can have again this. So the way that we usually think about things, that we have sometimes a decrease in concentration, but we would never have a decrease in concentration in time and then an increase again in regular chemicals. But here you can have, if you try to describe the concentration of your particulated form, of your ionic form. So we know also that they change accordingly to the environment they are in. There are parameters in the environment that change their behavior. And this is one of those examples. So this is a map from Europe, and here you have the distribution of water chemistry classes. So we have classified them from 1 to 6, and the 1 and 2 groups are representing the low ionic strength groups, where we think that there will be a higher stability of nanoparticles, and the groups 5 and 6 will represent the higher ionic strength, so the stability will be lower. Just looking at our country, we already know that the water type or the water class is different from north to south, and we can really see here that even in a very small country, we will have mainly huge differences in their behavior, in nanoparticle behavior, if they reach natural water. So the toxicities might be very, very different. So will this be true or not? Of course, it will depend on a lot of things, but our main aim is to make a cross on this. So our aim is to help out industry to run and produce new particles, safer particles, in a way that they don't prejudice, they don't harm the environment. So what kind of approaches have we done? First, we have all these parameters that need to be assessed. One that usually is a little bit forgotten is coating. So some of the coatings that are used in nanoparticles may induce some toxicity to organisms. And regarding the fact that they are released in time, so we need also to assess them. Usually we have mainly two controls in our assays, a negative control and a solvent control, where we need to use as a dispersal carrier, but now we have an extra one, the coating, so it's also important. Then the dissolution, usually what we have to do to quantify our exposure is to fractionate all the potential forms that we have in our exposure and quantify them to see how the behavior is going on time, and also the liberation or the negation state. The soil matrix, if we are evaluating soil, this is very difficult because we are trying to see nanoparticles in a complex matrix. So here we could see some nanoparticles by extracting water from soil, but even though the water that is extracted from soil has a lot of components, so sometimes it's also difficult to detect their presence in the soil, and just looking at the water in the soil is not the correct exposure for the majority of organisms that live in soil, because they also ingest soil particles, and some of the particles will be attached to the soil particles also. This is another example. I will show you a little bit further our exposures of silver nanoparticle in fish, and we expose them in tap water. And here is the behavior. We also assess the behavior of the nanoparticles in our tap water from Aveiro. And here you can see the freshly spiked nanoparticles, where we could see them individually dispersed, but then after 48 hours they start to agglomerate and start to get organic layer around them, so forming bigger agglomerates. So what we try to do by using our laboratory approaches is to simulate the real scenario. So here you have a real scenario where small fishes eat organisms that are on the top of the sediments. They are eaten by bigger fishes, and then we can eat those fish. So usually there is a transformation, an increasing concentration throughout a trophic chain, where the concentration is increasing in each level of the trophic chain and getting their highest values on the top predators. So this is called biomagnification, and is a concern regarding environmental contamination. So what we did is that we simulated a trophic chain from microalgae to a small crustacean that is called Daphnia to fish. So these algae are usually used to feed Daphnias, and the Daphnia are used to feed fish. So what we did is that we simulated what happened within a trophic model chain. So first, our first approach was to see how the algae were dealing with silver nanoparticles. These silver nanoparticles were very small. Their initial size was between 3 and 8 nanometers. And what we saw is, because we usually compare the toxicity of nanoparticles to the ionic counterparts to see if they differ or not. And what we saw is that their toxicity was very similar. This was not expected, because we also performed some toxicity testing with the daphne and the fish, and usually the salt was always more toxic, and this was a surprise. But we repeat the tests, and this is what we got. We continued testing further, and another approach that we did was to figure out what was inside the algae. But as you know, sometimes these processes of research, they don't follow as you wish, and this result only came a little bit later when we have already tested the daphnids exposed to contaminated algae. But then it was used to discuss our results. So what we saw here, and that is a pattern from the majority of silver nanoparticles, is that unicellular algae, or some species of unicellular algae like this one, cannot incorporate silver nanoparticles. So what this meant was that the toxicity was mainly induced by the dissolved silver that was coming out from the nanoparticles. Here we used a Raman car technique where we have, this was our control, so the unicellular algae with no silver. These treatments here were, the algae were dosed with nanoparticles, and then they were centrifuged and they were washed. So there were still some signs of nanoparticles outside the cells. And here was an approach that we did, that we dosed the algae, we centrifuged them, but we didn't wash them. So what we get was major agglomerates outside the cells. So we could never see nanoparticles inside the algae cells. So this was a problem when we thought that after going further into our trophic chain, that we will provide these algae that were previously contaminated with silver nanoparticles, but without any incorporation of nanoparticles. So, but when we did this, that we were feeding our daphnids with contaminated algae, the first step was that we were thinking we were feeding them with nanoparticles, but we were not. We were feeding them with algae with ionic silver inside, or at least dissolved. But what we did was that besides the contaminated food, we also provide them contaminated water with silver nanoparticles or the ionic silver. And what we saw here was that these are toxicokinetic approaches that we used for evaluating how the organisms can deal with nanoparticles. So mainly, this is an experiment in time. Here you have the concentration of silver inside the organisms, and here is the concentration that you get in time. So what we saw here is that the concentration that was being uptaken by the daphnids was much higher when the nanoparticulate form was present in the water than when it was present only as an ionic salt. And here are the bioaccumulation factors that were also higher for the daphnids exposed to nanoparticles. So we moved further and we did the same procedure, contaminated algae, contaminated daphne, and we feed the fish with these daphnids. And what we did exactly the same, those kinetic approaches, but with several organs from the fish: gills, liver, intestine, and muscle. And we also had a look at the kinetics. Here I'm only showing you some of the organs. First I will show you the liver. And our first hint was there is no elimination. So what happens here is that we were expecting that the fish were able to eliminate, to excrete the silver, but they cannot excrete silver, even if it's particulated or dissolved. Then in the muscle, that is the most interesting one for us, that we usually eat fish. Again, the elimination was very low or almost null, but there was a difference in terms of uptake and elimination if we have a look at the nanoparticle form or the nitrate salt. So there is being much more accumulated as a particulate form than as a dissolved one. So just to go a little bit quicker on these results, we also performed some approaches, now changing a little bit of pattern for graphene. Graphene was provided us by a researcher from TEMA. They use these two as a potential way of treating cancer cells. So mainly what they do is that they provide heating to the graphene, and the graphene will start increasing the temperature around the tumor cells and kill them. So what we did also was a very trying to simulate the approach by irradiating the graphene upon exposure to daphnes to see how they react, and we were very happy in terms of results because this graphene does not induce any hazard to daphnes or to zebrafish embryos, which was very good to know, even at concentrations that are completely unrealistic. So we increased the concentrations as much as we could, and even though there were no effects to the organisms tested, which is very good for them to proceed with the further studies and potential use in the future. So, and how do we use this information that we collect in the lab? So, we can just build up some curves like these. So, as much information as you collect from different organisms and different types of organisms, you can run a species sensitivity distribution that will rank your species in terms of sensitivity, and then you derive what we call hazard concentration for 5% of the species. This means that we are aiming at protecting 95% of the species. This concentration will be then used to be compared with predicted environmental concentrations. As for nanoparticles, there are not many studies that have analyzed real concentrations in the environment, so usually modeling is used to predict the concentrations, and what we do is that we compare the predicted environmental concentration used by modeling by the predicted no-effect concentration that is derived from the curves, from the species sensitivity curves that we did. If this quotient is higher than 1, there will be risk. If it's lower than 1, there will be no risk. So that's how we use the data that we collect from our lab. So I will just finish, and thank you very much for your time.
Thank you very much, Dr. Loureiro. Now there is time for just a short question.
So you are mainly interested in the trophic chain. But there is contamination of the soil.
Yes.
And the soil is very easily airborne. Is there any data about airborne nanoparticles and their effect on the organisms?
We have done several studies also on organisms. We have the same approach in this term of nanoparticles in silver nanoparticles also to some organisms that live in soil. And for silver is one of the most toxic particles for soil organisms and also for aquatic organisms. But we are doing also other approaches. We are testing zinc oxide also. We are testing the graphene to see how organisms can deal with this kind of approaches. But then going for trophic chains is difficult because then we will have to use vertebrates. And using vertebrates is ethically more difficult, and we need to get a really high permission to run this kind of tests.
And we have the coffee break next. We can allow for a short question more, and they come to the coffee break.
How do you predict the distribution of nanoparticles across
Across the?
across Europe? Japan.
Portugal is very great.
Very distributed. Yes.
No, there is the class, the chemistry class of water.
No. The last slide.
Here.
The green one.
Yes, this one. This one is the risk. So the prediction.
The one
This
before,
one.
yeah, that one.
This one is for soil, but this prediction is made by modeling, and they use as input data the number of people living in a country, the consumption they make of products with silver in this case, then the discharge that they model to that go into the wastewater treatment plants, and there are already some studies that.
Why are we orange?
Well, we are orange for several reasons that are not for here, but we are in this pattern here. Mainly there are some regions that make us become orange, like Lisbon and Porto.
Paris, no. Paris, Madrid, Barcelona.
Okay.
But it also has to do with the way that we treat our waste. Mainly is that reason. That is why Holland is white, because they don't incorporate waste into soils, they burn everything. So, and mainly the output is the way that we also treat the waste, because there are countries that are much more efficient than us.
Okay. Thank you very much. There is some housekeeping business now that I should announce. So we have the coffee break now, and we should come back at 10:30, meaning 10:25, so that we keep up to the schedule. And then we give